All right, get ready to dive deep because today we're exploring a fascinating physics paper, one that takes us to the very edge of what we understand about the universe. It's called, and get this, EFT, decoupling, Higgs boson mixing, and higher dimensional operators. Now stick with me because it's way cooler than it sounds.
Yeah, that title is a mouthful, but the ideas underneath are mind-blowing. It's like, imagine you're trying to figure out how a super complex machine works, but all you've got is like the most basic user manual. That's kind of where we are with particle physics. We've got this thing called the standard model, great starting point, but we all have this hunch there's a whole lot more going on under the hood.
So is this paper like trying to hack the machine code of the universe, going beyond the basic manual?
Exactly. They're diving deep into effective field theory, EFT for short. Think of it like a set of superpowered mathematical tools that physicists use to zoom in, weigh in on the tiniest bits of the universe. They're searching for clues about new physics stuff that goes beyond what we currently understand.
Okay, I'm liking the sound of this zooming in, but how does this paper actually do that? What's their approach?
They're focusing on something called Higgs boson mixing, and yeah, that's where things get really wild. You've heard of the Higgs boson, right? That particle that gives everything else mass.
Oh yeah, the rock star of the particle physics world.
That's the one. Now imagine the Higgs isn't just one particle, but it's part of a whole family of particles all jumbled up, sharing properties like some kind of cosmic mix and match. That's the basic idea behind Higgs boson mixing.
A particle party. Love it. But seriously now, why should we care if the Higgs has some long-lost siblings?
Yeah.
How does that change our understanding of the universe?
It could change everything. Seriously, Higgs boson mixing pops up in a bunch of theories that go beyond the standard model. We're talking about things like dark matter, why gravity is so weak compared to other forces, even the very fabric of the universe. These could all be linked to the Higgs having a way more complex family tree than we ever imagined.
Okay, now that's officially blowing my mind. But how does this paper actually test if our view of the Higgs needs an upgrade? What are they using as their microscope?
Great question. They're using something called oblique corrections. And no, it's not as scary as it sounds. Imagine light from a distant star traveling billions of years to reach our telescopes. On its journey, it passes through all sorts of stuff, planets, galaxies, maybe even invisible particles we haven't even discovered yet. And all that stuff leaves a tiny mark, a distortion on the light, kind of like a fingerprint.
So by studying those distortions in the starlight, we can learn about what the light passed through, even if we can't see those things directly.
You got it. It's like cosmic detective work.
Yeah.
And in this case, the researchers are looking for distortions that could be caused by Higgs boson mixing, a unique signature that points to these hidden particles.
Cosmic fingerprints. Now that's what I call a clue. But how do we know these fingerprints aren't just, I don't know, space dust or something? How do we separate the truly extraordinary from the ordinary?
And that's where the power of effective field theory comes into play. They're essentially building a super detailed mathematical model, like a simulation of the universe, to see how these distortions should look if the Higgs does indeed have these hidden relatives.
So they're comparing the fingerprints they see in the starlight to a set of theoretical fingerprints from their model.
Exactly. And here's the really interesting part. This paper goes even further. They take their model to something called dimension 8, which is like adding extra layers of detail and complexity, making it super sensitive to subtle effects. Think of it like upgrading from a basic roadmap to a high-res satellite image.
Okay, so more detail, higher resolution, better chances of spotting those cosmic fingerprints. I'm with you so far.
Right. And what they found is that going to this dimension 8 level, adding that extra layer of detail, actually changes the predicted fingerprint of Higgs boson mixing, especially for one type of potential Higgs sibling called a singlet scalar.
Now this singlet scalar sounds like the life of the particle party. But before we get into what they found, let's unpack this Dimension 8 idea a bit more.
Yeah, dimension 8 can be a brain bender for sure. In our everyday lives, we experience like 3 dimensions of space, right? Up, down, left, right, forward, backward. And then we've got time as our fourth dimension. But in effective field theory, dimensions get a whole new meaning.
Okay, you're going to have to break this down for me. What do dimensions actually mean in the world of EFT?
So it's not like we're talking about extra spatial dimensions, though that would be pretty wild, right? It's more about adding complexity to our mathematical models. Each higher dimension means we're getting more sensitive to those tiny effects from potential new particles and forces that we wouldn't catch otherwise.
So dimension 8 is like taking our Higgs microscope and cranking up the magnification, letting us see those superfine details.
Exactly. And what the researchers found is that when they zoomed in to that level of detail, when they included those dimension 8 terms, it actually changed how much they predicted this singlet scalar would blend with the Higgs boson.
Okay, so let's go back to that mixing angle for a sec. How can we even measure how mixed the Higgs might be with this singlet scalar? Is there some kind of cosmic recipe we missed?
Ah, if only it were that simple. The truth is, that mixing angle, how much the Higgs and the singlet scalar blend together, it's a free parameter in their model. They had to play around with different mixing angles, from just a tiny bit of mixing to almost the maximum the theory would allow.
So they basically said, what if there's a pinch of singlet scalar? What if we dump the whole jar in?
Yeah.
Let's see what happens.
You got it. And to keep everything from going haywire, they also had to factor in this really important concept called unitarity.
Unitarity.
Okay.
That one sounds a little intimidating, even for me.
It's actually a pretty elegant idea when you get down to it. Unitarity makes sure that the probabilities in their calculations always add up to 100%, because you can't have like 110% chance of something happening, right? That just wouldn't make any sense.
Okay, no probabilities gone wild. Gotcha. So unitarity keeps their model in check, make sure it reflects reality. Now, drum roll, please. What did they actually find? Did going to dimension 8 even matter?
This is where it gets really juicy. They found that for some values of that mixing angle, especially the larger ones, meaning a lot of mixing between the Higgs and the singlet scalar, including dimension 8 terms, made their model match up way better with the actual measured oblique corrections we see out there in the universe.
Hold on, so you're telling me that by looking at those starlight distortions with a stronger lens, by going to dimension 8, their predictions actually got closer to what's really going on in the universe?
You got it. It's like their models suddenly snapped into focus. Those little quirks they were seeing, the data actually started making more sense.
Okay, that's seriously cool. So does this mean dimension 8 is the magic key to unlocking all the secrets of the universe?
Well, I wouldn't go that far, but it definitely suggests that if we want to truly grasp those subtle hints of new physics hiding in plain sight, we might need to go beyond the simple stuff. We need to get up close, use our most sophisticated tools, and really pay attention. It's like realizing your map app was zoomed out too far, you were missing that massive traffic jam up ahead.
And in this case, that traffic jam could be pointing us to hidden particles, new forces, maybe even a whole new understanding of how mass itself works. This is why I love doing this. The intrigue is off the charts.
For sure. It's a great reminder that even in theoretical physics, we got to keep pushing, keep looking closer. Those tiny details, they can make all the difference.
And this paper focused on those specific light distortions, the oblique corrections, to test their model. But what if we looked elsewhere? Are there other cosmic crime scenes we could investigate?
Now, that's a question that's got the whole field buzzing.
So it's like we've been looking through one specific window, these oblique corrections, and we're catching these really faint signals.
Yeah, and the signals are saying, hey, there might be something really interesting going on here if you look closer.
Exactly. But what if we opened up some other windows? Would we see even more evidence that going to this dimension 8 level is important, for getting a clearer picture?
That's the million-dollar question. And it's got the whole field of particle physics buzzing, trust me. This research is really just the tip of the iceberg. We've got a whole bunch of other observables, other ways to peek into the subatomic world and see if our models are holding up.
So it's like they found a really intriguing piece of a puzzle.
Yeah.
But right now, we don't know where it fits in the bigger picture.
Perfect analogy. And that's what makes this so exciting. It opens up a whole new world of possibilities. What happens if we take this dimension 8 thinking and apply it to other observables? Could we uncover even more evidence for this singlet scalar particle? Or maybe we'll stumble upon entirely new particles we haven't even dreamt up yet.
Or uncover whole new mysteries we didn't even know to look for.
Yeah.
That's the beauty of this, right?
Absolutely. That's science in a nutshell. It's not about having all the answers, but about asking the right questions. This paper just reminds us that sometimes you got to zoom in, you got to use a more powerful lens to see what's really going on in the universe.
And we have those powerful lenses now, right? Like the Large Hadron Collider, these incredible machines that can help us test these theories.
Exactly. It's an incredible time to be a physicist. We've got these mind-blowing theoretical tools like EFT, and we've got these amazing experiments where we're smashing particles together at almost the speed of light. And we're doing it all to catch a glimpse of something truly fundamental, something that could completely change how we understand the universe.
It's like the universe is whispering its secrets and we're finally starting to listen.
And those whispers, those subtle hints in the data, they could be the key to unlocking the biggest mysteries in physics. We're talking about dark matter, the origin of mass, maybe even a deeper understanding of the fundamental forces of nature. It's all about pushing the boundaries of human knowledge, exploring the universe with a sense of wonder and a thirst for discovery.
Couldn't have said it better myself. And I think it's so important to remember, even though this research might seem abstract, it has the potential to really change our lives.
Oh, absolutely. I mean, think about it. So many of the technologies we rely on today, from medical imaging to, well, the very devices we're using to have this conversation, they all came about from understanding the fundamental building blocks of the
I think
universe.
that's right. So next time you pick up your smartphone or whatever it might be, remember those physicists hard at work, diving deep into their Dimension 8 world. They might just be on the verge of the next big breakthrough.
Because sometimes the most groundbreaking discoveries, they come from the tiniest details, from looking at the universe in a new way and never ever being afraid to ask, what if?
And on that note, we'll leave you to ponder the mysteries of the Higgs boson, extra dimensions, and the ever-evolving map of our universe.
Until next time, keep exploring, keep asking those big questions, and keep diving deep.